the most common way is to use a quartz crystal. We developed a series of MEMS which replace the crystal. MEMS is much smaller, it's much more resistant. The silicon supply chain is actually very, very reliable. SiTime is a company which specializes in timing. It is the only company in the world which does only timing and which really focuses on developing timing and bringing timing to the next level. In a digital system, timing provides a heartbeat. Like every transition occurs at the same time and so on. Yeah. Now in a data transmission system, timing drives the data transfer.
Okay.
Yeah. Like for instance in wired or in a wireless transmission, it's very, very important to have very good timing here. In a telecom system, it is very important to have a synchronization between the talker and the listener. And timing is all about this synchronization. So at SiTime, we used to describe that as precision timing. What you want to achieve is a certain frequency within a certain limit. And there are different ways of doing it, like the one very known way is to have an RC oscillator and so on. But by far the most common way today, and which has been like in the last 50 years or so, is to use a quartz crystal. A quartz crystal is based on like mechanical resonance of a crystal, a piece of glass, basically.
So, and its frequency depends on the size, I guess.
Yes, exactly. So if you want a crystal at 10 megahertz or if you want a crystal at 20 megahertz, it will be a different piece of crystal.
Yeah.
And then you have a resonator, which is the simplest part. You activate it, you excite it electrically, and it will oscillate at its resonant frequency. What we do at SiTime, we replace this crystal by a MEMS resonator. Yeah. So MEMS is all over the place those days. These are these micro-electromechanical systems. Yeah. And you can do quite a bunch of stuff with the MEMS. You can do microphone, you can do loudspeaker, you can do gyroscopes, you can do like the gyroscope of your cell phone, the accelerometer of your cell phone. We developed a series of MEMS which replace the crystal. So the MEMS will be the resonant part. The MEMS is actually the frequency reference.
Okay.
Yeah. So we have different MEMS resonator which oscillate at different frequencies, and then we use a PLL to convert that to the desired frequency.
Oh, okay.
So the MEMS has many, many advantages compared to crystal. First, if you look at a crystal, if you need any kind of frequency, you need to develop a new crystal.
Yes.
Okay. What we do, we go one step further. We use a so-called PLL, a phase-lock loop, to convert the frequency of the MEMS into the frequency you need.
Okay.
But then if you look at the resonator itself, a crystal has it's a piece of glass with a certain size, and this means it's kind of fragile. MEMS is much smaller, it's much more resistant. It's done on one piece of silicon, like the same kind of silicon which is used in semiconductor manufacturing. Okay. And this is one of the most resistant material on the world. It's a very, very good material actually. And one of the advantages as well is that it's very stable over temperature. If you look at a crystal and you subject it to temperature changes, the resonant frequency will change.
Yeah. Is it just from expansion and contraction?
Yes, exactly. Yeah. Same with MEMS, but to a much, much lower degree, almost inexistent.
Yeah.
Another advantage is that it is much smaller, much more resilient to shock, to vibration, and this is very important, for instance, for our aerospace and defense customers in environments where you have IG loads, like think smart munition.
I guess I never thought about how much force you can get in some of those applications.
Yes, exactly. And these MEMS are virtually indestructible. Yeah. What is that chip here? It is a device which we call Cascade. In its simplest form, it's a clock generator.
Yes.
Okay. Which means it's a bit like a big oscillator where you get a clock, you generate a clock, but you generate more than one.
Yeah. As
Easy
you
as
can
1,
see,
2, 3. It's neat.
yeah, up to 22 on this one, isn't it?
Yes.
Yeah.
You can also use it for synchronization. We talked in the first part about synchronizing like network, for instance.
Yeah.
So here you can get an incoming clock, and this incoming clock might have what we call jitter.
Okay.
Jitter is a very important parameter in the timing world. It's basically when your frequency slightly changes in a very, very fast way. And jitter can be very detrimental for like high-speed communication.
Yeah, because I guess things will just be out of sync just ever so slightly.
It's not so much about synchronization, it just increases your bit error rate of your link. Yeah. A bit wired or wireless, jitter is bad for that. For other applications, like for clocking a digital circuit or clocking a microcontroller,
not so much of an issue.
You wouldn't care about jitter, but in everything where you have high-speed link, jitter is very, very important. When you choose a timing device, you have to be sure that the jitter level generated by the timing device is below your the limit, which is usually set.
Otherwise, your device won't work reliably.
Exactly, it will not work reliably. So, and this is a great thing about that one is the jitter level is really good. If you want to clock a high-speed link, you want something with a low jitter. But you have this clock, you want to synchronize it too, and it has jitter. Okay, what do? This is where this guy comes in. So he takes some clock, you can synchronize on that clock, it removes the jitter, filters it. This is done by a special kind of PLL, which is called a jitter attenuator. And then you can output to whatever element you need a clock. You can change the frequency as well if you want. You can manipulate that. It's very, very flexible chip.
Where do you think is the ideal application that you think this would go into?
So for this is purely a telecom chip. You can use it, as I said, as a clock generator. It's possibly a bit too big for that for most applications. That's why there are also smaller clock generators. Contact us for more details if you are interested.
Yeah, I mean, if you want timing, just go to SiTime.
Exactly.
I could spend the whole year writing about all of their things.
If you look at the crystal industry, like the crystal blanks, as they are called, come from a couple factories, like maybe 2, maybe 3. I don't know exactly the number.
So it's one of those industries that there is actually a really small supply chain, and then it just goes out to lots of other people.
Exactly. The amount of manufacturer is really high, but the blank come only from a very limited amount of supplier. What we do here with SiTime, we use a pure semiconductor supply chain.
Yeah.
Okay. So our MEMS resonator comes from a Bosch factory in Winkelmuller in Germany, not too far from here.
Oh, nice.
Then we mix it with we couple it with a CMOS. The CMOS comes from TSMC in Taiwan.
Oh, okay.
And then we have several assembly houses, like 3 or 4 assembly houses, which can go in parallel for like more security of supply. But the great thing about the semiconductor supply chain compared to a crystal supply chain is that it's scalable. And we saw that during the last couple of years where there have been a lot of shortages, especially of crystals. Well, if you think about like our MEMS, for instance, we use like what we get from the Bosch factory is a 8-inch wafer, like about this size. And an 8-inch wafer yields 100,000 pieces of MEMS resonator, which is like, you know, in a box like that, you get 1 million pieces. And it's very easy for us to build inventory, to keep inventory just in case. And it's very easy to respond to a surge in demand. And so the silicon supply chain is actually very, very reliable.
Good. So that was a cool chat with SiTime on the ipXchange booth, which is why there was a lot of noise in the background. We do love making noise. Anyway, you can learn a bit more about the SiTime products in the pre-show article that I did with the links in the description. This isn't my car.